This problem is taken from the worksheet on systems of equations. It's question 6. So we're given a system of 3 equations, including two variables a and b. And we're asked for what values of a and b does the system have a unique solution, an infinite number of solutions, or no solution. By solutions here, they mean solutions for x, y, and z. So the first thing to do is to write down the augmented matrix. The first equation there reads x plus 2y plus z is equal to 1. So the first line of our matrix is 1, 2, 1, and 1. Same with the second line, 2, 5, 3. Now on here we have a, so that's just a. 3x plus 4y plus b times z, b goes in there, is equal to 9. Now we can proceed with the Gaussian elimination. So first step would be to get rid of this 2 and this 3 and make them 0. So to get rid of that 2, I'll want to take away twice the first row from the second row. So row 2 minus twice row 1 goes in here to row 2. To make that 3 into a 0, I'll have to take away 3 times that 1 on top. So it's going to be row 3 minus 3 times row 1 in there to row 3. So my first row here doesn't change. I have 2 minus 2 times 1 gives me the 0 that I was looking for. 5 minus 2 times 2 is equal to 1. 3 minus 2 times 1 is equal to 1. And a minus 2 times 1 is a minus 2. So that's the second row. We go on to the third row. So we're taking away 3 times the first row from the third row. So 3 minus 3 times 1 gives me the 0 I was looking for here. That 4 minus 3 times the 2 above gives me minus 2. b minus 3 times that 1 in the first row gives me b minus 3. And that 9 minus 3 times the 1 in the top row is 9 minus 3 is 6. Next, I want to get rid of this minus 2 and make that into a 0. Now I see that there's a 2 up here that I could use to get rid of this 2 here. But if I did that, then this 1 here would turn that 0 into something else, and I want to keep this 0 here. So instead I'll use the second row. That way that 0 here will leave this one alone. So I want to use this 1 to get rid of this minus 2. We'll say row 3 plus twice row 2 goes in there to row 3. So that'll get rid of that 2. So my first 2 rows are going to stay exactly the same now. That 0 is still going to be 0. That minus 2 minus twice the one above gives me the 0 I want here. Then I have b minus 3 plus 2 times the one above, which gives me b minus 1. That goes in here. Then I have 6 plus twice that a minus 2 above it, which gives me 2a plus 6 minus 4 is equal to 2a plus 2. And that goes in here. So that is Gaussian elimination done. So let's have a look at this last row here and see if we can figure out for what values of a and b we have what kinds of solutions. Let's start with a quick recap on the different kinds of solutions. So if after Gaussian elimination on my last row I have a row like this, let's say we have some numbers f and g here, right? Where f and g are not equal to 0, right? And this is whatever it is. That case is a unique solution, because there in that last row I have an equation that I can solve for z. You know, it would look like f times z is equal to g, and I could solve that for z in terms of whatever that f and g are. So that's the unique solution. The next possibility is that I have all zeros in here and whatever I have up there. Now if I have all zeros in there, if I get a 0 row on the left, that means that my original A matrix actually had a determinant of 0. And it means I either have no solution or I have infinitely many solutions. So the no solution case is where I have something in here, we'll call it g, and we'll say it's not equal to 0. That's no solution. The reason it's no solution is that that last line as an equation now reads 0 is equal to g, which is impossible. The third possibility then is that I have zeros all the way along the bottom row. So I have whatever I have up here, and I have 0, 0, 0, 0 down there in the end. That is the infinite set of solutions. So here's that matrix again that we ended up with after Gaussian elimination. So we can see that the first two rows are fine. No matter what A and B are, they're going to be fine, because there's no A's and B's on the left side there. It's that last row that has that B in there on the left side, that B minus 1. So as long as that B minus 1 isn't 0, we'll have a unique solution. Because as long as you don't get a 0 row on the left side of that augmented matrix, then we have a unique solution. So to answer part 1, we have a unique solution if B minus 1 is not equal to 0. So that's the same thing as saying that B is not equal to 1. And A here can have any value. Part 2 asks, when do we have an infinite number of solutions? Well, for that I need a whole row of zeros. So I need infinite solution if B minus 1 is equal to 0 and 2A plus 2 is also equal to 0. So that's how I get my row of all zeros that lets me take a free variable and get the infinite set of solutions. So B minus 1 is 0, means that B is equal to 1, and 2A plus 2 is 0, means that A is equal to minus 1. So that's my condition for an infinite solution. Part 3 asks, when do we have no solution? We have no solution if we have 0 on the left and something non-zero on the right. So that means we have no solution if B minus 1 is equal to 0, but the thing on the right is not equal to 0. So 2A plus 2 not equal to 0. So that implies that B is equal to 1, but A is not equal to minus 1. And that's my condition for no solution, is that B is 1 and A is any number except minus 1. So to summarize, if B has any value except for 1, then I have a unique solution, or I get a last row like this, where F and G are not equal to 0. That's the unique solution. The next possibility is that, let's say B is equal to 1. Then I either have infinite solutions or no solution. And I get the infinite solution if A is exactly equal to minus 1. So that's where I get a last line that looks like this. I get those zeros. So that's where B is 1 and A is equal to minus 1. But if B is just 1 and A is some other number except for minus 1, then I end up with a last line that looks like this. I have some other number there, where G is not equal to 0. That's what you would call inconsistent, an inconsistent set of equations for which there is no solution. So that's the answer. Those are my 3 cases and my 3 conditions. The last thing we're asked to do is to obtain the solutions in case 2, where it's an infinite number, and confirm for z equal to 2. So we'll do that now. So we're looking at case 2, that's B is equal to 1 and A is equal to minus 1. So now I'll rewrite my matrix with that in mind. So we have 1, 2, 1 and 1, 0, 1, 1. We have A minus 2 there, so A is minus 1, so I have minus 1 minus 2 is minus 3. 0, 0. If B is 1, B minus 1 is 0. And if A is minus 1, I have 2A plus 2, which comes out to be 0. So that's what I expected for this case with an infinite number of solutions, because now I have my row with all zeros on the left and on the right. So this is where I introduce the free variable. I'll call my new free variable t, and I'll say it's just any real number. And then my solution for z is just z is equal to t. Now I can substitute that back into the second row. that second row as an equation reads y plus z is equal to minus 3. So I'll substitute back in that z and I get y plus t is equal to minus 3, or y is equal to minus 3 minus t. And then I substitute back again into the first row. So as an equation, that first row reads x plus 2 times y plus z is equal to 1. Substituting back in my values, that comes out to be x plus 2 times minus 3 minus t plus t is equal to 1. So that implies that x minus 6 minus 2t plus t is equal to 1, or x minus 6 minus t is equal to 1, or x is equal to 7 plus t. My final solution then is that x, y and z is equal to 7 plus t minus 3 minus t and t, where t is any real number. The last thing we were asked is to confirm for z equal to 2. So z is equal to 2, well that means t is also equal to 2. So that means y is equal to minus 3 minus 2 is equal to minus 5, and it means that x is equal to 7 plus 2 is equal to 9. We are asked to verify that that is a solution. So here is the original set of equations. So let's just check that that is a solution. So that first one, x plus 2y plus z is equal to 1. Well, x is equal to 9, so we have 9 plus 2 times y is minus 5 plus z is 2. That's equal to 9 minus 10 plus 2 is equal to 1. So that's right. That's that first one checked. Now the second row, 2 times x, which is 9, plus 5 times y, which is minus 5, plus 3 times z, which is 2. That's equal to 18 minus 25 plus 6 is equal to minus 1. And we see in the equation that that's a, but we have from before that a is equal to minus 1 in this case. That was the condition for the infinite solution. So we're good. That's that second one checked. Lastly, 3 times x, which is 9, plus 4 times y, which is minus 5, plus b times z, which is 2. Well, we have from before that b is actually equal to 1. That again was a condition. So 3 9s are 27 minus 20 plus 2 is equal to 9. So that one is right. So we've confirmed there that if we set t equal to 2 and we get z equals 2, y is equal to minus 5 and x equal to 9 from our solution on the top, that does actually solve the set of 3 equations. So in a case where a is equal to minus 1 and b is equal to 1, that's just one of an infinite set of values for x, y and z that would solve those 3 equations. Now in a test you won't actually be asked to verify your answer at the end, but everything up to that verification point is very relevant to your exam. So if you didn't understand what went on there, go back and watch it again, or if you still don't get it, ask me tomorrow in the tutorial. So that's it for now.